AI, AI, AI. It seems we can't go 10 seconds without hearing another thing about AI. And I guess I'm just adding to the problem. Some of us love it, some of us hate it, but I think that everybody should try to understand it, at least at an intuitive level of how it works underneath the hood. Because I think there's a lot of fear right now around AI, and I'm not here to state whether that fear is justified or isn't, but I do think it's worth it to try to just understand how it works underneath the hood. And in this video, what I want to do is kind of explain some of the mathematical underpinnings of it without getting into the nitty gritty details, just sort of at an intuitive level, and also distinguish it from other types of technology that we've been using for a long time. And it's right now the word AI kind of gets thrown into everything, and it's not clear exactly what is AI and what isn't. So I kind of want to clear all of that up in this video. Okay, so let's start with what isn't AI. Okay, I don't know, take a calculator, for example. A calculator obviously is smart, feels smart, but that's not AI. Let's take another example. Take Google Maps. You can tell Google Maps, like, hey, show me how to get from where I am to this address. Now that feels pretty smart, but that's still not AI. And the difference is that for something like Google Maps, it's really just following a set of steps that a human programmer programmed into the computer. So for example, what Google Maps does is it has all these different cities. It has their maps sort of represented as graphs, like what I am showing here. It's just a set of nodes and edges. Maybe let's say that the nodes represent intersections and the edges represent roads. The number on the edges might represent how long the road is, or that might also factor in the traffic at that particular time at that road. And when you tell it, hey, I want to get from point A to point F, there's a set of steps that are going to start executing that could be represented by a flowchart or by computer code. And those steps might say like, okay, you're on node A, look at the outgoing edges, take the shortest one out. And then when you're on that node, consider the different edges. And then, a set of steps that I won't go into because they're not relevant to this video. But the point is that it can be represented by a flowchart. And the flowchart was designed by a human. And by simply following that flowchart, which may branch off into different branches, it may have looping logic to repeat things, but ultimately the flowchart was designed by a human, and the computer is just blindly following those steps. And at the end of executing the flowchart, it arrives at the answer. This is the best path from where you are to the address that you're asking to go to. That's not AI. I'll give you an example of something that is AI. Imagine giving an image to a computer and asking, is this a dog or a cat? Now, for humans, that's very easy to do. But for a computer, that's not easy to do. How would you write a flowchart or computer code to look at an image and say whether it's a dog or a cat? Remember that an image to a computer is just a table of pixel values, and those pixel values are just numbers at the end of the day. So you have this giant table of numbers that are an image of a dog or a cat. How are you going to write a computer program or a flowchart to determine whether it's a dog or a cat? The dog could be any breed, it could be looking in any direction, it could be a cartoon dog. Again, to a human, this is very easy, but to a computer, this is extremely difficult. And to my knowledge, nobody has written a traditional computer program to do that. But we can use AI to answer that question. And the way to successfully do this is not to write traditional computer code and tell it like, oh, look at pixel 0, 0 and compare it to pixel 10, 10. Like that won't lead you anywhere. Instead, what does work is a technique called machine learning, which is a field of AI, which is really the field of AI that's producing everything we're seeing nowadays. And machine learning consists of learning from examples or experience. So if you wanted to learn to distinguish dogs from cats, what you might do is gather a data set of millions of pictures of dogs, millions of pictures of cats. All those pictures should be labeled, very importantly. The pictures of dogs should have a little label that says dog. Pictures of cats should have a label that says cat. And then you show all these examples to the computer, and the computer can learn to kind of find patterns such that you can then show it a new picture of a dog that wasn't in the training set, and it will successfully determine that that's a dog. And in this video, I'm going to explain how that works. Okay, so just to recap, traditional software, which includes pretty much everything you had used before the ChatGPT moment, not everything, but most things that you had used before the ChatGPT moment, I would consider traditional software. And behind the scenes, the computer was just blindly executing a set of steps that a human programmer wrote. Those set of steps are called the computer program, and that's it. That's traditional software. Machine learning, specifically supervised machine learning, what the human programmer does is not to write steps to achieve the task. Instead, the human programmer sets up a way for the computer to learn from examples. So we'll get into that in the next slides. So let's start with something that everybody's familiar with. It's called linear regression, and it is a type of machine learning, a very simple type of machine learning, but it is machine learning. So suppose you want to teach a computer to predict the price of a house given the area, the square footage of that house. Now, if you wanted to do it in a traditional software way, you might say, oh, well, the area divided by 10, or actually maybe multiplied by 100, is the price in dollars of the house on average. And sure, that's fair enough. You could kind of just write a computer program to do that. But if you wanted to do it through machine learning, the first step that you would need to do is to gather a lot of data points of real houses, their square footage, and their price. And you could plot them like this. Okay, that's the first step. Now, the first thing you'll notice is that there's an upward trend that could probably be captured by a line. And so you, as the machine learning practitioner, decide, okay, I think this pattern could be represented by a line. And so you draw the line of best fit. And now that you have a line of best fit, if we're talking in machine learning terms, the line is your trained model, which now you can give it a new house area that wasn't in its training set, but it can now predict what it thinks the price of that house is. So this is a form of machine learning because the computer code that was written wasn't explicitly made to predict price based on square footage. Instead, the computer code was written to, given a set of data points, find the line of best fit. So that's what the computer code did, but the end result is that we now have a model that can look at a square footage and predict the price. And that's very similar to what a machine learning model does when it's given an image of an animal that it's never seen, and then it predicts whether it's a dog or a cat or a mouse or some other animal. But before we get into those other modalities like images and text, let's stick with just numbers for a little while longer because there's a lot we can learn from simple examples like this that we can then later apply to more modern machine learning. Okay, so let's consider our prediction of house price again. You know, given the square footage, given the area, predict the price. Let's look at it a little bit more closely now. We had said that the first step was to gather data points, which we have here. And then we said the next step is draw a line of best fit. Well, the question is, how do you find that line of best fit? Obviously, visually, as humans, we can just kind of draw it in our head. But a computer, you need like an algorithm, you need a set of steps to find that line of best fit. So in other words, you know, out of all of these potential lines, the blue one, the green one, the red one, you know, which is the right line, which is the one of best fit. Now you may remember from algebra class in school that a line can be defined by two values, m and b. M represents the slope, so like how inclined is it, and then b represents like at what value does it cross the vertical axis. So with these two values, you can define any line. And then the question is like, what are the m and b values that result in the line of best fit? So the way to find that line of best fit is that we kind of start with this blue line. It's the fact that it's placed right now as the best line of best fit. You don't know that initially. You're kind of just starting with a line whose m and b values are unknown, and then you write a formula that measures the vertical distance from each point, from each data point, from each training point to this unknown line. And then you take each of those vertical distances and you square it. Okay, that's what this little 2 here means. You square it. Visually, you can think of that as like making a square where all sides are of that distance. And then you add up the area of all those squares and you try to minimize that. Okay, the line of best fit is going to be the line where if you do this, where you measure the vertical distance to each data point and then you square that and then you add up all those areas, the line of best fit is the one that minimizes the sum of those squares. Okay, and this formula here, what it represents is the sum of those areas. And all the y1s and x1s and y6 and x6, all of those are known values. So really the only two unknown values in this formula are m and b. So you have a formula that is in terms of m and b, and so you can graph that, and that's what we have here. This is the b-axis, this is the m-axis, and then this vertical axis represents like what is the sum of those square values. The shape that it makes is kind of like this bowl shape that has a minimum, it has a bottom where the sum of squares is minimized. And at that bottom, there's a specific b and m value that minimize that. And though that's the b and m value that define the line of best fit. Okay, and we can use calculus that you may remember from school. I'm not going to go into the details of it, but you can use calculus to find the bottom of that bowl and therefore find the b and m value that give you the line of best fit. Now you may be wondering why I'm going into this level of detail, but it's just because all of this is going to be very directly applicable to understanding what's going on when we extend this to, modern AI, not just linear regression. Okay, now let's use another example because this is going to help me illustrate another important point. Suppose that now, instead of predicting the price of a house based on its area, we wanted to predict the temperature in a given city given the month of the year. So this is not linear anymore, right? It's kind of curved because at the beginning of the year it's winter, in the middle of the year it's summer, at the end of the year it's winter again, so the temperature goes down. And so a line like this red one doesn't really capture the data well anymore. Now what you want is a curve, which mathematically can be represented by a quadratic equation. Importantly, the quadratic equation now has 3 parameters, a, b, and c, 3 unknown values that we need to find if we want to find the curve of best fit, unlike the line which only had 2 parameters, m and b. So a, b, and c are parameters. In machine learning, it's also common to call parameters weights. You may have heard about open weight models. They're referring to these types of weights, these types of parameters. Now imagine a data set that had a more complicated pattern. It's kind of curved in many places like this. Well, we can still find a curve of best fit, but it's no longer going to be a quadratic equation with 3 parameters. It might be an equation with more parameters, maybe 5 or 6 parameters, and that will allow us to represent the data better. So the important lesson here is that the more parameters you add, the more flexible our model becomes, the more complex data the model can represent. So yeah, here in the first example, it's a line, 2 parameters, it can only represent linear data. 3 parameters, you can now represent curved data. 4 parameters, and you can represent more complicated curved data, etc., etc. Okay, so we've been learning about different types of models, lines, curves, more complicated curves, and said that the more parameters you add, the more complicated the data that can be represented by the model. And I just want to tie this back to how you may have heard in the news, especially in the early days of modern AI. You might have heard about, GPT-3 is a model with 175 billion parameters. And GPT-4 is rumored to have this many more parameters. Like I said in an earlier slide, parameters are sometimes called weights, and you also sometimes hear the term open weight. So DeepSeek is a Chinese company that makes models, and their models are open weight. What that means is that, that M and B value that we found through calculus that represents the line of best fit, that M and B value are the weights, and the Chinese companies are making those weights open. They're sharing with the world, hey, we trained our model, and then these are the values that are the best fit ones. Okay, so let's get into more modern stuff. What you're looking at here is called a neural network. Um, Behind the scenes, ChatGPT, the Claude models, all of them, they're not using lines and curves like we've been looking at. They are using neural networks. Um, this architecture is inspired by the human brain, where these little nodes represent the neurons in the brain and the connections between them represent synapses. It's really just an inspiration. Obviously, the human brain works quite differently, but it's an inspiration. And while this looks complicated, at the end of the day, this entire thing is just a math formula. So how is it a math formula? Well, each of these nodes right here is a little math formula like this. Okay, we take a max operation, so we take the larger between 0 or this. And then x1, x2, x3, x6, up to x6, it's the inputs to this node. So you can see how each of these nodes here are x1, x2, x3, x4, and they're all connected to each of the nodes in the next layer. And each of these nodes, they apply this formula. They take the incoming value x1 and multiply it by a parameter a, the incoming value x2, multiply it by a parameter b, etc., and then add all of that up, and then do a max operation, comparing it to 0. So this entire neural network has this formula at each node, and each node has its own version of A, B, C, D, E, F, etc. So the entire neural network, the entire math formula, has a lot more parameters than the curves we've been looking at. A real neural network would have more layers than this, and each layer would have many more nodes. So that's how you end up with a GPT model that has billions of parameters. It's just these A's, B's, and C's, and D's, and F's, etc. Okay, so you probably have a bunch of questions, so let me take them one at a time. So a first question you might have is the following. All the models we had been looking at up until now took a number as an input and spat out another number as an output. So for example, the input was the square footage of a house, and then the output was the price of that house. But with this neural network, or this math formula, the input is an image, and then the output is a classification. Like, this is a dog, or this is a cat, this is a mouse. So how do we go from number input and number output to image input and classification output? And the answer is quite simple. Remember in an earlier slide I had said that an image to a computer is just a table of numbers, where each number represents essentially the numeric value of that color for that pixel. So all we do is we take each pixel and we pass it into one of the nodes in the first layer of the network. And then the computation flows through the network in the way that I described in the previous slide, where each node just takes all the incoming values, multiplies them each by a parameter, applies a max operation, and then passes that output value into each of the nodes in the next layer. And then at the end, when the network wants to express, hey, I think this is a dog, or I think this is a cat, or I think this is a mouse, it just outputs 3 numeric values, which are kind of percentages. So essentially here it's saying, I'm 87% sure that this is a dog, I'm 5% sure it's a cat, and I'm 8% sure it's a mouse. So yeah, that's how you take an image as an input and then output a classification. So another question you may have is like, okay, I get it. Once you have a network with weights that work, you can pass in an image and it can output what it thinks it is, whether it thinks it's a dog or a cat or a mouse. But the obvious question is, how do you learn those weight values? How do you find all those A, B's, and C's and D's such that the network can correctly do this? Take in a random image of a dog it's never seen before and correctly identify it as a dog. How do you find those weight values? And it turns out the answer is pretty similar to how we found the M and B parameter values when we were trying to predict the house of a price given its square footage. So remember that when we were predicting house price from house area, the first step was to collect a bunch of examples of real houses, their area, and their price so that we could plot them. Similarly, now that we want to predict, given an image of a dog, cat, or mouse, predict whether it's a dog, a cat, or a mouse, the first step is to gather a bunch of examples. We want lots of images of dogs, lots of images of cats, lots of images of mice, each labeled with what it is. Okay, so once we've gathered all those training examples, what we're going to do is we're going to initialize our network with random weight values. Okay, all those A, B, C's, and D's, they're initially going to be small values close to 0 that are randomly initialized. And we're going to take our first example, we're going to pass it into the network, pixel by pixel, like I had described earlier, and we compute the entire network, right, with all those random weight values. And then what we're going to get is the neural network's guess. It's 33% sure it's a dog, 35% sure it's a cat, 32% sure it's a mouse. It's wrong, obviously. It thinks it's a cat, and its certainty is very low because the 3 percentages are very similar. But here's where the label comes in, right? All those training examples that we gathered, they're labeled. So we know that this is a dog, and we know that the correct answer is this in green. It's 100% sure it's a dog, 0% sure it's a cat, 0% sure it's a mouse. And what we now do is we kind of compare the neural network's guess with the correct answer, and we compute a number that says like how wrong was the neural network. The function that kind of compares these three numbers with these three numbers and says how wrong was the neural network, that's called the loss function. And it's similar to when we were doing the house thing, when we were predicting the line of best fit. Our loss function there was the sum of squares. Remember that? Our loss function in this case is a function that says, you know, how different is the neural network's guess from the correct answer. And then what we do is we use calculus to say how, like for all of these thousands of weights in the neural network, for each one individually. So like take the first A in this node. If I move this A up just a little bit, make it a little bit bigger, will it make my network's prediction better or worse? If moving it up makes it better, then move that weight up, or that parameter value up a little bit. So the B in this node. If I move that up, does it make my prediction better? Or if I move it down, does it make it better? And then if moving it down makes it better, then we move that weight downward. But we just take a tiny step in the right direction. So just to recap, we take our training example, we pass it through the network, we see its predictions, we compare it to the right answer, we compute a number that says like how wrong is it, and then for each weight in the network, we tweak that weight slightly just to make the prediction a little bit better, such that after that weight update, if we were to pass in this example through the network again, the predictions wouldn't be right yet, but they would be better. So maybe cat would go down to 33% and dog would go up to 35%, which is a little bit better than the original prediction when we had random weight values. Then we take out our next example. This time it's an image of a cat, and the correct answer here in green says, yeah, that's a cat. You should be 100% sure that that's a cat. So yeah, we take this second example, we pass it through the network, same as the first one. We get a prediction. It's wrong. In this case, it thinks it's a mouse, and the percentages on all three are very similar, but it thinks it's a mouse. It's wrong. So we compare that to the right answer, and then we look back at all the weights in our network, and we say, we tweak each one, some of them up, some of them down, but each weight, we tweak it in the direction that will make this prediction better, that it'll move it in the right direction. And then you take your third example. Maybe the third example is a mouse. You pass it through, you compare the guess with the right answer, you update the weights to make it a little bit better. And then you do that over and over and over again with all of your examples. Millions of dogs, millions of cats, millions of mice. The result, after making all those weight updates over and over again, is that into these weights gets encoded a sort of understanding of like, what is a cat, what is a dog, what is a mouse, and how to identify it from an image. It's a sort of knowledge that we would never be able to program into a traditional computer program or like a flowchart. Because like I had said earlier, you're never going to write a computer program that says like, look at pixel at coordinate 1010 compared to pixel at coordinate 1212. You're never going to figure out what's a dog and what's a cat that way. But by this repetitive process of updating all these weights, the weights encode this knowledge, and by the end of it, you can input into this neural network an image of a dog that wasn't in the training set, so a new dog, but the weights will have seen so many dogs and that learn to kind of extract details about that dog or features about that dog, such that the network will now see a new dog that it's never seen before and correctly output a prediction that will maybe say like 98% sure it's a dog, 1% sure it's a cat, 1% sure it's a mouse. So I just want to give some of this a name. So this process of taking your training example, computing it forward through the network, seeing how wrong the prediction was, and then kind of going backwards through the network and seeing, okay, if I modify this parameter up or down, is it going to make my prediction better or worse? And then modifying that weight value. That is called backpropagation. Okay, it's a very important algorithm in machine learning, specifically in neural network training. It's called backpropagation, and it's an application of calculus, very similar to when we were looking at the linear regression, how we use calculus to find the bottom of that bowl and then find the m and b value that got us the line of best fit. Backpropagation is an application of calculus, and it's very similar to that. And so this slide kind of visualizes that. So on the left, we have linear regression. We had talked about this earlier. We use calculus to find the bottom of the bowl, right? The bottom of the loss function, the m and b values that minimize the sum of squares. So in other words, the m and b values that get us the line of best fit. So that's linear regression. For neural networks, it's more complicated than that. You can see that the shape of the graph is not a simple bowl. Instead, I like to call this like a loss landscape. Okay, there could be many peaks, many valleys, and the loss landscape itself, where all the peaks and valleys are, is defined by your training samples, okay? And then where you're standing on this loss landscape, so whether you're at a peak or whether you're near a valley at the bottom, that's kind of defined by your current set of weight values. So similar to here on the left, on the linear regression, if your m and b were very wrong, you might be in one of these red sections where your sum of squares is huge, so your line of best fit isn't a best line, it's kind of like really wrong. Similar on the neural network, at the beginning when we haven't trained our weight values, we might be near the top where the error is very big. Our neural network is not predicting things well. But each time we show it an example and we shift the weights of the neural network in the right direction, it's like taking a little step down the loss landscape. And then we show it another example and we shift the weight values to improve the prediction, and we take another small step down the loss landscape. And you repeat this over and over again, and you slowly move down the loss landscape until you reach kind of the bottom where your neural network is now making very small errors. Remember, the vertical axis represents the error. We started with high error, and hopefully by the end we have very low error, and our neural network is making very good predictions. So the neural network might say, I'm 99% sure that it's a dog, and the right answer was 100% sure. Well, that's very close. The error is very small. I just want to add a couple of points. The first one is that this algorithm of like slowly moving down the loss landscape, that is called gradient descent. The name makes sense, descent, you're moving downward. And you'll hear that term a lot because it's very important in machine learning. And then the other point I wanted to make is that in the linear regression case, there was 3 dimensions, right? One was the b value, one was the m value, and then the vertical dimension was the sum of squares. How wrong are you? And so when you just have 3 dimensions, you can easily visualize that. In the neural network case, this is actually a bit of a simplification because, like I said, the vertical axis represents how wrong are you, right? Like how wrong was the neural network's prediction? And so fine, one vertical axis. But the other two axes I mentioned represent your current weight values. Where are you standing on the loss landscape? But obviously, we don't have just 2 weight values. We have billions of weight values. So the real loss landscape is in a much higher dimensional space than just 3 dimensions like this, but we can't visualize that. So just to think about it, we put it in 3 dimensions. I just wanted to clarify that. Okay, now I just wanted to give you an example of how this can be applied in real life. Suppose that, just from historical data, you have a lot of medical scanning images of people who turned out at the end to be healthy and people who turned out at the end to have been sick. So now you have all these medical images of, this scan, this person ended up being healthy, this scan, this person ended up being sick, and you have many of those. Well, that's labeled data. So you could actually train a neural network to, based on all that data, and then now a new patient comes into the doctor's office, they get a scan, and then you pass that scan through the neural network, and the neural network tells you this scan is healthy or this scan is sick. Now, what we've seen in practice is that these AIs, these neural networks, can actually detect illnesses in medical imaging, sometimes much earlier than a human. But in the case of cancer, I've read articles where an AI identified cancer years before a human could have seen that medical imaging and identified the cancer. So this is a very exciting application of exactly what I just explained to you. Now, I've emphasized that the labeled part of the data is very important. It's no good to have thousands of images of dogs and cats and mouses if they're not labeled, right? Because you saw that to correct the weights of the network, you need to compare the network's output prediction to the correct prediction. That's why you need a label. And this is just actually a little fun fact. So when you're logging into websites and they tell you to identify the traffic lights, identify the cars, identify the crosswalks, identify the pedestrians, they're not trying to check if you're a human. What they're getting you to do is label images so that they can train their AIs potentially for self-driving. So that's just a little fun fact. Okay, so we've studied how a neural network can be used to classify images. But what about text, right? Because after all, the big important moment was when ChatGPT was released, and that wasn't about classifying images. That was about a text interface where you could send messages, get messages back. So how does that work? Remember how I explained how you can take an image and pass it into a neural network by just passing in each individual pixel value? And then I also explained how you can output a classification by basically outputting percentages. Here, I'm going to make a claim that just like you can pass in an image, you can also pass in text. And just like you can output a classification, you can also output a word, a single word. I'm not in this video. I'm not going to prove that claim, but in the description, I'll leave a link to another video that I'm going to make where I'll go into more detail there. But I just want to keep this video focused, and so I don't want to kind of detract from the main storyline. So just accept for now that you can pass in text and output a word using this same neural network architecture. Specifically, let's consider a neural network that can take in 100 words. Here I just have 3 words, but let's suppose that was 100 words, and that network outputs 1 word. Okay, now I haven't explained yet how we're going to find the weights or anything, but just the dimensions of the neural network can take in 100 words and output 1 word. Now, remember when I was talking about the labeled images of cats and dogs and mice, and also when I was talking about the Google authentication where you have to identify the crosswalks, the traffic lights, etc. I mentioned that one of the most challenging parts of machine learning is finding enough labeled data to train your network, because you need a lot of data to train neural networks. And it's often not difficult to just find raw data, like images of dogs and cats and mice, but labeled data is harder to come across. And so in the case of text, scientists had this interesting idea, which was, we have all this like tons and tons of text on the internet. What if we kind of try to make a model that's good at predicting the next word? So I got this random Wikipedia article just to say, what if as our first 100 words we take this blue part, and then given that we try to train our network to predict the next word? So that's one training example, right? This is the data point, and then this is the correct label, is the next word. And then you just shift this over by 1 word, and the next bit becomes your next training point. And the next word becomes your next correct label. And then you basically do this with like all the text in the internet. So you have tons of data to train on. You have tons of data to train a network that's very good at predicting just the next word after a sequence of words. So just to visualize that very clearly, whereas before the input was an image of an animal and the output was like a classification, now the input is like a piece of text and the correct output is just the next word. And then, like I said earlier, we just shift it along by one word at a time, teaching the network to always predict the next word. And we have tons of training data, all the text on the internet. So once you've trained a neural network to be very good at predicting the next word, guess what? You now give it a new piece of text. Hello, how are? And then it's learned to predict the next most likely word, and it says you. I just want to point out that this is what we call a large language model, an LLM. It's large, it's for language, it's an AI model, it's an LLM. It just predicts the next word. So we've arrived at the ChatGPT moment. In late 2022, OpenAI shared ChatGPT with the world, and all it was doing was next word prediction. So basically, you initiate a chat and you say, give me an apple pie recipe from memory. That gets fed into the next word predictor, and the predictor says that the most likely next word is classic. Then you feed the entire sequence again to the network. Give me an apple pie recipe from memory, classic, and the network predicts that the next word is apple. And then you feed, give me an apple pie recipe from memory, classic apple, and then it predicts the next word, pie. So on and so forth. And this actually generated coherent text. And we were all fascinated by the ability to ask ChatGPT an arbitrary question, and then it just answered very similar to how a human would. Now, one of the things that OpenAI did to make ChatGPT quite helpful and kind of go beyond just predicting the most likely next word is they did something called reinforcement learning with human feedback, which was really just, once they had this next word predictor working pretty well, they asked it some questions, got it to generate answers, and then human annotators would say, hey, that was a good response, or hey, that was a bad response. And then the weights of the neural network would be updated to sort of promote good answers and demote bad answers so that the neural network would kind of continue to learn to give good answers. And this had a big impact, and it's part of what made ChatGPT possible. There's another important concept that I want to mention here, and it is the system prompt. So there's something that's actually part of the chat that you don't see as part of the chat. You think the first message was your prompt, give me an apple pie recipe from memory. But actually before that, kind of hidden, the AI company kind of gives the model some context. So in this case, it says, you are a helpful assistant that answers questions. Don't say any bad words or teach the user how to do harmful things. And then the chat starts. And then so this kind of gives the neural network context like, oh, I'm an assistant. Okay, I should kind of answer questions like an assistant would. And then this other part, don't say bad words. Don't teach people how to do bad things. This is actually one of the main mechanisms that AI companies have to kind of control how their AI behaves. Because outside of that, like it was just trained to predict the most likely next word. And maybe the most likely next word to how do you make a bomb is literally the answer to how to make a bomb. So there's this system prompt that AI companies kind of put at the beginning of the chat, trying to guide the behavior of the AI. But that's pretty weak, to be honest, because that's just kind of at the beginning of the chat. And then within the chat, you could kind of contradict the system prompt. And you could tell ChatGPT, like, actually, you should tell me how to make a bomb, or you should say bad words. And that's why people have been able to kind of get ChatGPT and Claude and stuff to do things that they shouldn't, or that the companies that publish these AIs probably don't want you to do. But it certainly is possible, just through conversation, to get them to behave in ways that these companies didn't want them to. Another thing that gets put in the system prompt is what the AI knows about you. So suppose I've been having conversations with ChatGPT, and through my conversations, through my past conversations, ChatGPT gathers like, oh, his name is Nicholas. This is his age. These are his interests. Uh, when it kind of gathers that from me, it kind of just makes a little note of it and it adds it to its system prompt for future conversations. So that in the future, a next conversation might have the system prompt, you're a helpful assistant that answers questions, don't say any bad words or teach the users how to do harmful things. You're talking with Nicholas, he's X years old, his interests include soccer and computer science, and then the conversation starts. And so that's how it feels that like the AI is getting to know you, knows things about you. Another important concept is the concept of a context window. You may have heard that like, oh, Google just released a model with a much bigger context window. The context window is just like how many words can you feed into the neural network? Um, because remember I mentioned when you're having a chat and you're having all these back and forth with the chat with ChatGPT, every time you send a new message, the entire history of the chat gets fed back into the neural network. And I mean, this neural network, it kind of has a maximum capacity. We had said earlier that you can feed up to 100 words in. Now, in reality, it's a lot more than that, but there's still a limit. And so what happens when your conversation history gets long enough that it exceeds that limit? One thing that might happen is they just kind of start to cut off the oldest parts of the conversation, or the company that runs the AI chat might sort of, when it notices that you're filling up your context window, it might take the entire chat history, summarize it using an LLM, but it'll summarize it. And so your conversation history kind of gets compressed. That's why you might notice that if your conversation with AI is long enough, it maybe starts to get a little bit dumber. It's because its context window is filling up, and maybe even the first parts of your conversation are not even in the context anymore. This is also why it's good to, if you're going to start talking about a completely new topic, just start a new conversation because the context window gets cleared. Okay, another concept that I want to touch on is the idea of reasoning models or chain of thought models. Those words might ring a bell, but it was in late 2024 that OpenAI came out with the O1 model. And what they realized is that their models were giving better answers if instead of just kind of being fed in the user prompt and then immediately start spewing out the first words that the neural networks predicts, if instead they kind of gave the neural network some time to just output tokens that aren't going to be part of the response. They're just thinking tokens. So I don't know. You might ask the chat you might ask ChatGPT, what's the best way to make spaghetti? And so it might, before it answers, think for a few seconds and be like, oh, well, what are all the ways that I might make spaghetti? What are the pros and cons of each? And then after it's kind of reasoned for a while, then it'll finally give the final answer. And this turns out to be very effective for tasks that require reasoning, that would require a human to do reasoning, right? Like math questions, programming things. They found out that it's useful to literally let the model reason in the form of spitting out tokens and thinking about it that way. Okay, now the next thing I want to explain is agents, right? Because initially it was just a chat interface, you could talk back and forth with it, but increasingly you can ask AIs to do things for you, not just answer questions, but like do things for you. It's not unreasonable nowadays to ask something like Claude Cowork, like, hey, go check my email, find the email that Cheryl sent me last week, download the spreadsheet that she sent me, make some nice graphs and visualizations for it, and share it with my team on Slack. And then it goes and does all of that for you. So how is that possible? The first thing you need to understand is that, as you go about your day and you use your computer, you're using a bunch of services. I don't know, let's call it like Excel is a service, PowerPoint is another one, Gmail is another one, Dropbox is another one, YouTube is another one. And you're using the human interface or the user interface to interact with all of these services and all of these tools. But all of these tools also have an application programming interface, an API, and it's a way to interact with that service or that application through code. And this has nothing to do with AI. This existed before AI, but through code, you could check your email. Through code, you could modify a spreadsheet. So that exists. And because LLM's training data doesn't just include text, but it also includes code, LLMs are very good at coding. And so they can use these APIs to interact with all those services. They can use these APIs to interact with Excel, with Gmail, with Slack, with basically anything. Okay, so given that you have this thing called an LLM, which is very good at predicting the next word, how do you turn this into an agent? The type of thing that can do things for you, like send an email or book a flight or whatever. The first thing you're going to need is a harness, okay? And a harness is just normal computer code, the type that existed before AI, but it's going to be what orchestrates this entire process. So let me walk you through an example. The process starts with the user, Nicholas, sending a prompt that says, can you help me book a fun vacation? The harness, in green, is going to prepend a system prompt and then feed that into the LLM. So let's look at the system prompt. You are a helpful assistant. You're speaking to Nicholas, a guy that likes adventure vacations. The AI knows that and has that in the system prompt because of what I stated earlier, right? It puts things that it knows about you in the system prompt. So the system prompt says you're speaking to Nicholas, a guy that likes adventure vacations. If you need to execute code, output it between a set of square brackets. If you want to respond to Nicholas, output it between curly braces, followed by the prompt that I had sent. So Nicholas says, can you help me book a fun vacation? So this whole thing, the red and the black, gets fed into the LLM. And then the LLM starts predicting the next words. And it says, Nicholas likes adventure vacations. Let's see what flights are available right now. And then between square brackets, so it's trying to execute code, it writes the code to get the list of flights that are available right now from Expedia.com, a website that it knows is good for booking flights. So the LLM responds with this, and then the harness, which is just blindly following instructions, but it knows that if it sees square brackets, it needs to execute the code inside of the square brackets. So the harness executes this code, and that gets sent to Expedia, the flight booking website, and Expedia, with its API, right, the interface for interacting with it through code, responds with the available flights. There's flights available to the Amazon jungle, to Paris, to London, and to New York. So the harness feeds the full conversation history, including the Expedia result, into the LLM. So we're going to feed into the LLM like the full conversation history, the system prompt, Nicholas's prompt, the LLM reasoning, the response from Expedia. That's all gets fed into the LLM and asks the LLM to just predict more words. And then the LLM says, out of the options, because it's reading these options from Expedia, out of the options, Nicholas would probably like to go to the Amazon jungle because it knows that I like adventure vacations. And so in square brackets, it wants to execute more code. In square brackets, it writes code to book that flight. And then the harness sees that the LLM output square brackets, so it executes the code inside of the square brackets, and that code books the flight on Expedia. And Expedia replies with a success response, a success code. The harness then feeds all of that back into the LLM, the entire conversation history, the response from Expedia, this bit of reasoning here, and then finally the success code. Feeds all of that into the LLM, and then the LLM outputs, great, the booking succeeded. And then in curly braces says, Nicholas, your flight is booked. Curly braces because the system prompt had said that if it wants to speak back to Nicholas, it should output that in curly braces. So it does that. Nicholas, your flight is booked. And so I, as the user, I just saw that I sent it, can you help me book a fun vacation? It did all this work behind the scenes that I didn't see, and then it just replied with, great, the booking succeeded. Or rather, it replies with, Nicholas, your flight is booked. Now, there could be even more steps in there. It could send me a confirmation email. It could send a message to my mom, whatever. All of that could be done through putting code in square brackets. And that's it. I didn't realize the video would be that long, but hopefully it gives you that intuitive understanding of how these tools work underneath the hood. I focused on LLMs and agents, but in the news you're probably seeing about other types of AI, like image generation models, video generation models, robotics stuff. That wasn't the focus of this video, but what I can tell you is that a lot of the underlying technology with all of those types of things are what you learned about here. Like they all use neural networks, and they all kind of leverage this idea of a neural network can learn to do pretty much anything as long as you give it enough examples. Um, and that applies to generating images, generating videos, robotic stuff. If you're really interested in the robotic stuff, I suggest you look into a field called reinforcement learning, where the neural network, instead of just learning from labeled data, it, it learns from experience. So by interacting with the real world, it learns from experience and then updates its weights that way. But that's a story for another video.